All right, I guess we should start on time. Okay, so today I'm going to talk about Dicke models and some generalizations. So the plan of the talk is just like the title suggests. The first part, maybe 2/3 of the talk will be on the traditional Dicke model. I will provide some historical background and introduce some of the standard tools, theoretical tools to study the Dicke model. And then for the remainder of the talk, I will talk about some generalizations, which my group is involved in. All right, so it all started in 1954. Robert Dicke wrote this paper. He wants to understand what happens to the spontaneous emission of an ensemble of atoms. We know that for a single atom, the spontaneous emission is of excited atomic state is a fundamental property of the atom. So he wants to understand what happens if we have not a single atom, but a bunch of atoms. And you can imagine that initially all the atoms are in the excited state, and they will decay, jump back to the ground state and emitting photons. And let's assume that initially there is no correlation between these atoms, so these atoms are all independent from each other. And there is assume that there is no bare atomic interaction between the atoms. But it turns out that due to the fact that all these atoms are coupled to the same electromagnetic vacuum, correlation will build up during the emission process. So even though initially all the atoms are uncorrelated, independent, but as time goes on, the correlation becomes important. So instead of a exponential decay, so this dashed curve here is the spontaneous emission of a single atom or a bunch of independent atoms. If there is no correlation at all during the process, you just imagine that the spontaneous emission pattern should follow the single atom spontaneous emission pattern, just multiplied by number of excited atoms. But instead, what you see is this solid curve. You see a strong pulse, a big burst of emitted photons, and the peak of the intensity scales as n squared instead of n, and is the number of atoms. And of course, the width goes like 1 over n, so the total energy is still conserved. And so this is termed as super radiance because this very intense pulse. And it turns out that this phenomenon can be at least qualitatively understood from a very simple model. We can write down what we now call the Rabi model of a two-level atom coupled to a single mode optical field. Of course, for spontaneous emission, you actually need to consider multiple modes instead of a single optical field. But let's start from the simplest example we have. So it's just a two-level atom, a ground state and excited state, and the transition frequency is omega 0, and you can see my mouse. And the photon frequency is omega c, and the coupling between the atom and the photon is written in this form. Basically, you can consider this as the electric dipole interaction Hamiltonian minus d dot E. D is the electric dipole moment, and E is the electric field of the photon. And you can generalize this to n-atom models, and this is typically called the Dicke model. Okay? And we assume that all these different atoms coupled to the same field with the same strength, so the coupling is uniform, and so we just simply sum over all the atoms. Okay? So instead of the single atom Pauli matrices, the two-level atoms, so can be regarded as spin half particles. Use Pauli matrices to describe them. And for n atoms, we just have these collective operators, J's, and these are also angular momentum operators, obey angular momentum operator algebra. Joseph?
Why does your coupling strength scale 1 over square root of n now?
Oh, Well, you can scale everything as you want, but the thing when writing down the Dicke model, people typically single out this square root of n is, I don't think we have a, in the single particle, in the single atom coupling strength is G in the when you quantize the optical field. The G is proportional to the square root of 1 over V. V is the quantization volume. Okay. And so when I pull down this square root of n, I also include a square root of n in the definition of lambda. Okay. So in the lambda, you have square root of n over V. Okay. And that quantity is well defined in the thermodynamic limit when we take both n and v to infinity, but n over v is finite. Okay. So in writing this, lambda will be a finite quantity in the thermodynamic limit. Okay. And both the Rabi model and the Dicke model have so-called Z2 symmetry, and this is a manifestation of the so-called conserved parity operator. Okay. The evenness or oddness, the parity of the excitation number is conserved. The excitation number itself is not conserved in these models, but the parity is conserved. Okay. And it's obvious that the Dicke Hamiltonian commutes with J square, the total angular momentum operator. And therefore we can consider angular momentum state, the atomic states with specific J values separately. And particularly the largest J value you can get is n over 2. Each atom is spin half, so n atom together, the largest angular momentum you can get is n over 2. And historically, this largest J manifold will be called Dicke manifold, Dicke states. Now you can imagine that the state JJ, why am I writing this in terms of the angular momentum eigenstates? And for given J, the largest magnetic quantum number you can get is J itself. So this is the stretched state. So all the atoms are in the exact state, all spins up. And this, of course, is a unentangled. It's a product state. Okay, all the atoms. So the total state can be written as the product state of each single atom. Now imagine that one photon is emitted. So one of the atoms has to flip its spin to downspin. But since all these atoms uniformly coupled to the same field, we don't know which atom emitted the photon, which atom flipped the spin. So democracy wins, we have to sum over all possibilities. So assume that the ith atom flip spin become down, and we need to sum over all the i's from 1 to n. Okay. So I'm not taking care of the normalization factor, but that's fine. And the state written in the angular momentum form is a J minus 1.
Sorry, what's the meaning of these two J's here?
Oh, this is just angular momentum eigenstates Jm. So the first J is the
angular quantum number and the magnetic quantum number.
Yeah, magnetic quantum number.
But
so it's
the JZ is not commuting with H here, so.
Yeah, so only the J is only J square commutes with H, not JZ. Yeah. So the first quantum number J is associated with its eigenvalue of J square, and that does not change. But the second quantum number can change. And if another photon is emitted, then another atom has to flip its spin, and again, we have to sum over all different, so one pair of atoms flip its spin, we have to sum over all different pairs. Now you can see that these states are actually entangled. You cannot write them as product states. So this can go all the way down to when all the atoms flip a spin. And in the angular momentum language, this is the J minus J state. So only the top and the bottom states are product states, and all the rest of the states are actually entangled. And the properties of these Dicke states, the Dicke states can be generally written in this way. Again, writing this in the angular momentum eigenstate form, and these Dicke states are fully symmetrized. So Jm state contains J plus m up spins and the rest down spins. And you can show that you can define a squeezing parameter to characterize the spin squeezing property of these Dicke states. And there are a few definitions of squeezing parameter, and this is one particular one. And under this definition, the squeeze state is when this quantity is less than 1/2. And it has also been shown that spin squeezing is intimately connected to quantum entanglement, and the entanglement depths, meaning how many atoms are entangled, are related to this squeezed parameter in this particular way. And now you can show that when m is less than n/2, these Dicke states are squeezed. And if m is much less than n, the squeeze parameter scales as 1/n. You can actually approach Heisenberg limited metrological sensitivity. And when m is less than square root of n/2, the entanglement depth is on the order of n. So all the atoms are essentially entangled. Okay, so these are some of the interesting properties of Dicke states themselves.
So if n is just like 1, don't I also have things entangled?
M is 1?
Yeah.
Yeah, well, m is 0 is the middle state. Yeah. So m is 0 is in the middle of this chain, and that's the most entangled state.
Oh, but don't all of them have an entanglement depth of like the full?
Not necessary, no. No.
Like in the J-1 state,
Yeah.
there's no unentangled spin, right?
Well,
This state is exactly the Doppler state.
yeah. So the entanglement depth is not. The entanglement depth is actually pretty shallow for this state. It's, and well, I don't know. If, maybe there are different definitions of entanglement depths.
I see.
Just like there are different definitions of spin squeezing.
It's very small, yeah.
I see.
Yeah. Okay. So Dicke wrote his paper in 1954, and almost 20 years passed. Then Hepp and Lieb started to got interested in the static properties of the Hamiltonian, because Dicke considered this transient dynamics, the superradiance dynamics, and Hepp and Lieb wrote this paper in Annals of Physics, and they want to understand the ground state and the thermodynamic, the static properties of the system governed by this Hamiltonian. And they show that the system supports a second-order phase transition, now what we call the superradiance phase transition. And so this is in 1973, and Hepp and Lieb's paper was written in a way that is very mathematical. And in the same year, Wang and Huey revisited the problem, studied the same problem, but use a language that is more understandable by common physicists. And so the idea is to calculate, well, this is thermodynamic, it can be finite temperature. So you need to calculate the density matrix, and Z is the partition function. And if we know how to calculate the partition function, then many of the thermodynamic properties can be calculated. For example, the free energy is just a proportion to the log of Z. And so how do we calculate the partition function? Partition function is the trace of this exponential operator. So to calculate the trace, you need to find a basis set. And it turns out that a convenient basis state is this product state with atoms and the photon. The atom states are just these product spin down, spin up states, and the photon state is the coherent state. And it turns out that the coherent photon basis is much more convenient than Fock state basis. So in the end, you have to calculate this, you sum over all the spins and integrate over the photon field. And long story short, you can show that in the end you end up with with an integral like this. It's still quite complicated, but in the thermodynamic limit, when number of atoms n goes to infinity, this integral can be calculated analytically using the Laplace method. So you get a nice expression for z, and from z you can calculate free energy, and from free energy you can determine the phase of the system. And so it turns out that there is a critical coupling strength, lambda c, when lambda c is given by this. It's square root of omega 0 times omega c divided by 2. If the coupling strength is below this threshold, then the system is in the normal state for all temperature. And the normal state is characterized by the fact that the average photon number, the ratio of the normalized photon number, normalized by the number of atoms. Again, everything is in the thermodynamic limit, where you need to take n to be infinity. In the normal state, this quantity is 0. And if lambda is larger than the critical coupling strength, then there exists a critical temperature, which is given by this. If T is larger than the critical temperature, again, this is the system is in the normal phase. And if temperature is below Tc, you enter the superradiance phase, so where this normalized photon number is finite. So that means the photon mode is macroscopically populated. And so you can draw a phase diagram like this. You have this is temperature, this is the normalized coupling strength. You have a normal phase here, you have superradiance phase here. And this phase transition goes all the way down to equal to 0 when it becomes a quantum phase transition. And it's a typical second order phase transition. So in the normal phase, you can typically take the order parameter as the expectation value of the photon annihilation operator, again normalized by square root of n. And in the normal phase, the order parameter is 0. In the superradiance phase, the ground state, the system become two-fold degenerate. The order parameter become finite. And the normal phase obeys the Z2 symmetry, and the superradiance phase break the Z2 symmetry, and the two states are Z2 symmetric to each other. Okay, so this is the so for my talk, I'm going to focus not on the dynamic of superradiance phase transition. I'm going to focus on the ground state and the static properties of the Dicke Hamiltonian and the superradiance phase transition. And later on, people figured out that there is actually a more convenient way of doing the calculation if you just want to understand the properties of phase transition of the Dicke model. You can do the so-called Holstein-Primakov mapping. And this mapping is actually exactly, you can map the angular momentum operators to bosonic operators. So this B and B dagger is bosonic operators. These so obey the bosonic commutation relations. And of course, it is valid when the term under the square root is non-negative. And of course, the square root become are not easy to handle with. So if you can make the approximation that I can ignore the B dagger B under the square root, then things become simple. And again, I take J to be n over 2. This is the Dicke manifold. So this approximation is valid when the photon, well, this is not a photon number, when this auxiliary bosonic excitation number is much smaller than n. And in that case, the raising angular momentum operator is just proportional to B dagger, and the lowering operator is proportional to B. And of course, this condition means this is valid in the normal phase, because this means that Jz is roughly equal to minus n over 2, which means all the atoms are in the ground state. And for the superradiance phase, this approximation is not valid, but there is a way to overcome this limitation. So under this mapping, you can rewrite the Hamiltonian we can get rid of all the j's and rewrite this in terms of b's. And so the Hamiltonian can be written in terms of two sets of bosonic operators, A and B, A dagger, B dagger. And the Hamiltonian has a quadratic form. And a quadratic bosonic Hamiltonian can be exactly solved using the Bogdanov transformation. And so I think maybe I can, well, so you can find a linear transformation, transform A dagger, B dagger to two new sets of bosonic operators, C1 dagger and C2 dagger. And you require that when rewrite the Hamiltonian in terms of C1, C2, only diagonalized terms exist, all off-diagonal terms vanish. And this will help you determine what this matrix, what this linear transformation should look like. And from this, we can find the excitation energies, E minus and E plus. Okay. There are two branches. Okay. And they can be, so there are analytic expressions for this. And of course, in order for this Hamiltonian to make sense, these excitation energies has to be non-negative. Okay. And the upper branch, E plus, is always well-behaved, real and positive, but E minus may dip down to 0. And to prevent that, you have to make sure that your lambda is below this threshold. And this threshold is exactly the critical coupling strength where the system enters the superradiance phase at t equal to 0. And as I mentioned that this approach I just outlined would work for the normal phase, okay, but for superradiance phase, you have to do one extra step, and you first displace these bosonic operators, and these alpha and beta will be found in a self-consistent way. They are of order n. And after that, you can exactly follow the same procedure, and you'll find a different form of the Hamiltonian, which is also quadratic in these bosonic operators, which can also be diagonalized, and you also find two branches of excitations. And these also have nice analytic expressions, and to make sure that they are well behaved, the lambda have to be larger than lambda c. So everything is self-consistent. This means this works in the superradiance phase. And to plot them together, you can see that these are the two branches of excitation as a function of coupling strength lambda. Here I copy paste this plot from this paper. Here 0.5 means the critical coupling strength lambda c. So at the critical coupling strength, the lower excitation branch dips to 0. And this again is a typical behavior for a continuous phase transition. And you can also find these scaling exponents of excitation gap, which is just the E minus, and also scaling behavior for the order parameter. All right. Okay. And you can also not only you can obtain the energy spectrum, you can also find the wave function directly. And in fact, this Hamiltonian can be regarded as a Hamiltonian of two coupled harmonic oscillators. So, for example, you can define two sets of position and momentum operators, xpx, y, py. And rewrite Hamiltonian in this way, we have two harmonic oscillators, but they are coupled together. And you can decouple them to find these normal modes, and the Bogdanov approach procedure is exactly the decoupling of these coupled oscillators. So after decoupling, you'll find that so these Q1, Q2, P1, P2 are two new pairs of position momentum operators. Again, now you can see that the Hamiltonian can be written as two independent harmonic oscillators. And with this, you can write down the ground state wave function, because we all know the ground state of harmonic oscillator, they are just the Gaussians. And so this is a product of two Gaussians. And so this can be written in terms of Q1, Q2, but I can rewrite this as a function of x and y. And you can plot out these wave functions. And more importantly, you can calculate the entanglement properties. For instance, you can trace out the photonic degree of freedom, and calculate the reduced density matrix for the atom. So it amounts to do this integrate over x. X is related to the photonic degree of freedom, and y is the atomic degree of freedom. And from this, you can calculate the atom-photon entanglement, which is just the von Neumann entropy of the reduced density operator. And you can show that in the thermodynamic limit, the atom-photon entanglement diverges logarithmically at the critical value. All right. And you can also study the squeezings, and you can show that in the if I consider x and y, you can show that my eyes are failing me. This is px. Px has a little bit of squeezing, and here the squeezing means below 0.5. Okay, the fluctuations below 0.5. But if you do it a slightly more clever way, you can define a new bosonic operator C, which is a linear combination of A and B, and with parameterized by this angle theta, and you can find out the optimal value of theta such that this quadrature is maximally squeezed. And turns out that the squeezing is perfectly at the critical value, and meaning fluctuation vanishes for this particular quadrature. All right. And finally, we can also add dissipations. We can consider that the system is coupled to an environment, and in the normal approximation that we assume the environment, the bath is Markovian, and so you can write down these Lindbladian mass equations by adding these dissipation terms to the Liouville equation, and these L's are the so-called jump operators. So depending on what kind of bath you have, what kind of dissipation channel you have, you have different L operators, different jump operators. For instance, if you have cavity decay, then the jump operator is photon annihilation operator. If you have a collective atomic decay, then the jump operator is S minus. Well, in my notation, it's J minus. And these two dissipation channels will not destroy the permutation symmetry of the atom. So in a sense, they are easy to handle. But if you have a single atom decay and a single atom dephasing, then the nice permutation symmetry between the atoms is broken. So things become slightly more complicated. And well, if we consider these two easy decay channels, cavity photon decay and collective atomic decay, so consider this the normal phase effective Hamiltonian, and adding these decays, writing down the mass equation, then you can derive the equation of motion for these operators. It can be written in this matrix form, and from this you can identify the threshold for superradiance, which turns out to be when the determinant of this matrix is 0. And from that you can find what is the critical coupling strength. So the critical coupling strength will be shifted due to these decay channels. Okay, so you have both photon decay kappa and atomic decay gamma. Okay. So the critical coupling strength will be increased in comparison to the Dicke Hamiltonian without dissipation. And if we consider a limit, if we ignore the atomic decay, just to consider the photon decay, and in the limit that the photon decay is very fast, so kappa becomes very large, such that the photon population will never build up. And in that case, we can eliminate the photons and writing down a factor Hamiltonian with only atomic operators, only with J's. And so under this limit, the effective Hamiltonian will take this form. And this is so-called LMG model. And LMG model was proposed in the 1960s in the context of nuclear matter. But you can see that it actually can be realized using these AMO systems. And the superradiance phase transition can also be understood as a composition of these two terms. Okay, so you can consider this like a quantum magnet. And the first term is a paramagnetic term. It's an external field along the z direction. So it tends to align the spin along the z direction. And the second term is Jx squared. So it tends to align the spin along the x, either x or minus x direction. And when the coupling strength lambda is small, the first term wins. So the atom is polarized along the z direction. It's a normal phase. And when lambda exceeds the critical value, the second term wins, and the spin will be aligned along either x or minus x, and this is the superradiance phase. Yeah.
So are we still just picturing this as like one big collective spin operator?
Yeah. So because
Jx squared just be identity up to some, because it's the sigma x squared identity.
No, Jx is not sigma x. Jx is the sum over all sigma x.
So we can't treat it as an actual angular momentum operator.
It is an angular momentum operator because it obeys the angular momentum commutation relation. Yeah.
One question. So even without any decay, we still integrate out the photon to get the effective energy.
Without decay, there are different limits that you can obtain as LMG models, even without decay. That's right.
There is some dynamic, but I think the leading order approximation has that.
Yeah, you can use.
I think the universality class of the phase transition are the same.
For instance, under some limit, you can eliminate the atoms and write down your effective Hamiltonian as using purely photonic operators A and A dagger, and then you use HP Holstein-Primakov mapping to rewrite these photonic operators in terms of spins, and it will have a similar form as LMG model. Okay, and another thing seems my computer is frozen. Yeah, I should also mention that, well, typically we think about phase transition, quantum phase transition, or classical phase transition as a property of a thermodynamic limit. In the Dicke model, the number of atoms had to go to infinity. But it turns out that even for finite n, even for n equal to 1, so for n equal to 1, the Dicke model reduced back to the Rabi model. And even for this case, you can still have a phase transition in the so-called classical oscillator limit when the ratio of the photonic frequency and atomic frequency approaches 0. And the properties of the phase transition are the same for Rabi model under this limit and the Dicke model in the thermodynamic limit. And as we mentioned, that the Dicke superradiance has been realized in experiments in various platforms, and of course the canonical realization of these models is to put atoms inside a cavity. Even though the Dicke model was proposed in the 50s, 70s, but its realization really took a long time, and it's not done until 2010s. And Dicke model has been also realized in superconducting qubit systems, in Professor Connell's group in these quantum magnets, and also in trapped ion systems. So you can realize, well, in different platforms, of course, the physics detail will be different. For example, in trapped ions, we do not have photons, but we have phonons. It's the phonon will play the role of photon that coupled to the spin, and the Hamiltonian looks similar to the Rabi or Dicke model. And in the case of quantum magnets, it's the spin coupled to the magnons, for instance. All right, so this finished the first part, and next I will talk about some generalizations of Dicke model, particularly those generalizations that my group is involved in. And one generalization is, instead of a single cavity system, you can consider multiple cavities. And these cavities are coupled to each other through photon hopping. So photons can hop between adjacent cavities. And in this work, we consider a 1D ring. So we have periodic boundary condition. And so for inside each cavity, we actually have a single atom. So it's a Rabi model. And the photons can hop between nearest neighbors. And you can even engineer a complex hopping amplitude characterized by this phase theta. So it's like you can synthesize a gauge field for the photons. And without going through all the details, after some transformations, after another HP mapping, you can write the Hamiltonian. You can write down a effective Hamiltonian in terms of only the spin operators. And the first line is the same Hamiltonian we'll get for the Rabi or Dicke model. This is the LMG model. And the other two lines arise due to the photon hopping between different cavities. And the second line corresponds to a XY exchange coupling. It tends to align the neighboring spins along the same direction, either X or Y, in the XY plane. And the last line is the so-called Jaroshinsky-Moria coupling term, or DZ term. And this is proportional to the cross product of the spins, so it tends to make the spins, neighboring spins, not collinear to each other. Okay. And so this quantum optical model can be mapped to a magnetic models, and these photon atom couplings, properties of phase transitions can be understood as competitions between all these different magnetic terms. And this phase diagram for 4 cavities and 3 cavities, it turns out that there is a kind of even odd effect. So we have a normal phase, but the superradiance phase becomes much more interesting because it has several superradiance phases, and you can classify them according to how the spins align themselves, whether the ferromagnetic or antiferromagnetic, or even form some kind of a chiral pattern. And another generalization you can do is in the Dicke or Rabi model, we consider 2-level atoms. But of course, for real atoms, you can have many atomic levels. So why not exploit more atomic levels? And we can generalize this Dicke model to consider a general atomic system with L levels. And so this HK is this is the case for the case atom, and H is the bare atomic Hamiltonian. It's a generalization of sigma Z. And this DK is the dipole operator for the case atom. So it's the generalization of sigma X. And so with more atomic levels, you have more control parameters, and turns out that the normal to superradiance phase transition can instead of being second order in the conventional Dicke model, now it can have higher order phase transitions. So you can have multi-critical points. And the reason why these are interesting is generally these multi-critical points have different behavior, differ with different orders, will exhibit different critical behavior. So, and also in many-body systems, it's pretty difficult, pretty rare to find high-order critical points, and the higher the order, the more constraints you need to satisfy. It's become more difficult to locate where these multi-critical points are. And it turns out that for this Dicke model with multi-level atoms, not only you can find these where you can actually analytically pinpoint where these multi-critical points are.
Well, how to understand the multi-level atoms? So for these operators, can I think of this as SU generalization or higher speed generalization?
Yeah, there is. Yeah, indeed. Let me give one example. This is a 3-level atom, and so we have 3 atomic levels, and we consider 2 transitions: a transition between 1 and 2, and a transition between 2 and 3. And this is the form of the H matrix, and this is the form of the D matrix. And the transition is characterized by 2 strengths, G and G gamma. And this gamma is a dimensionless number. Just it's the ratio of the ratio of the 2 transition strengths. So you can consider this as the generalization from SU2 to SU3.
But I think in the 2-level case, you already don't have coefficient symmetry. You just have J squared.
Mm-hmm.
You don't have the full set of SU2 generators.
Why?
Because
Well-
JZ is not connected with H.
That's true. It's not necessarily SU2 symmetric. Yeah.
So
And
in this context, how many good quantum numbers?
well, depending on specific D's and H's you take. Yeah. In general, we don't have many symmetries. But for this particular model, you can draw a phase diagram like this. We have a normal phase, you have superradiance phase, and the phase diagram is characterized by 2 quantities, this gamma here, and this normalized coupling strength G. And the phase boundary, you can show that there is a second order boundary. A part of the boundary is second order, part of the boundary is first order. And these 2 boundaries will join at the tricritical point. And the tricritical point can be calculated analytically given by this. And you can also study the scaling behavior and indeed the scaling exponents across the tricritical point will be different from the exponents across other points along the second order boundary.
How to understand the first order when gamma is very low?
Well, if gamma is large, okay, in my drawing, if gamma is large, you can ignore this upper transition. So it reduced to a 2-level system, so you should recover the conventional Dicke model, so it should be second order. But if gamma is small, then this transition becomes important. You expect things to be different. And why it becomes first order? I don't know if we have a simple picture to see
So
this.
actually expect there is a symmetry between small gamma and large gamma. So if gamma is near close to 0, then effectively it's also
I think it also depends on the ratio between omega and G.
Yeah, no. If gamma is 0, not necessarily. Because if gamma is 0, then this level 3 becomes a dark state. You have to. It does not reduce to the conventional Dicke model. All right. So my final thing is adding the atom-atom interaction. As I mentioned, that in the traditional Dicke model, we do not have direct atomic interactions included. even though the photons can induce some effective all-to-all atom-atom interaction. But now let's consider what happens if we add direct interaction between the atoms, and one particular simple interaction is these Ising couplings. Okay. And previously, people have done calculations including these Ising couplings, and recently, you guys also did some work along this line, and the system still has Z2 symmetry, so we can directly compare with the conventional Dicke model. And of course, in the limit that J equal to 0, this is the Ising coupling, we recover the Dicke model. And in the limit that the G is 0, this is the photon-atom coupling, we have the transverse field Ising model. And both the Dicke model and the transverse Ising model transverse field Ising model has been well studied, and they both feature second-order phase transitions. And so, inspired by this, we can define two order parameters: the Dicke parameter, which is the expectation value of photon annihilation operator, and so here we consider a antiferrometric coupling. So J is positive. So we have the antiferrometric, the staggered magnetization as the Ising order parameter. And this particular Hamiltonian can actually be solved analytically. You can consider a Jordan-Wigner transformation, Jordan-Wigner mapping to map the spins to free fermions, and with this you can write down the ground state energy. You can also do a finite temperature calculation, as we did in our paper. The ground state energy of at t equals 0, ground state energy is given by this this integral. In fact, from the point of view of Ising model, you can consider that we have two transverse fields. One is a static transverse field, so we have a static field with strength By, and another one is along the x direction. But this field is not static; it's a dynamic, okay, because it's a cavity field, and the cavity field is a dynamical field. And you can actually find this integral can be done analytically in terms of elliptical functions. Looks pretty complicated. But in any case, you can draw a phase diagram, ground state phase diagram like this. The phase diagram is characterized by two-dimensionless quantities: the normalized photon-atom coupling and the normalized B field. And so we have two order parameters. And for the Ising order parameter, we can have paramagnetic or antiferromagnetic orders. And for the Dicke order parameter, we can have normal phase or superradiance phase. But turns out that for the coupled system, we have only 3 phases. Okay. We do not have a antiferromagnetic superradiance phase. Okay. They are not. These two order parameters are not compatible with each other, and you can show mathematically why they are not compatible. So we have two normal phases. One is antiferromagnetic, and the other is paramagnetic. So in the normal phase, of course, we can the effect of photon is not important, so we can ignore this. So it's basically reduced to a transverse field Ising model, and for the superradiance phase, it's always paramagnetic. And we can understand that in the limit that By is large. If By is large, we can ignore the Ising coupling. So this reduced to a Dicke model, so we have a second-order phase transition. But when By is small, when this J term is important, the transition is first order. Okay. And again, the first order and the second order boundaries were joined at a triangular point. This is the point C. And also in this phase diagram, another point is also quite special, this point B. So this is the end point of this Ising boundary. So it's a critical endpoint. And this critical endpoint has some unusual properties. Now, if we focus on the on the neighborhood of B. Okay? We can expand the ground state energy around B, and you can see that it cannot be written as a nice Landau power series because you have these, and the reason is again at B, the Dicke order parameter will have a phase transition, will change dramatically, change abruptly, and that so there's some non-analytic behavior of the order parameter here, and that's why the ground state energy cannot be written as a nice power series. And if we consider a scan just above B, like along this line, you can show that it's a first order phase transition across this dashed line. So both order parameters, both the Ising and the Dicke order parameter, will have discontinuous jump. Okay. And you can also calculate spin susceptibility, spin entanglement. It has discontinuous jumps across this dashed line, but nothing blows up. Okay. It's a first order phase transition. It's not critical. However, if we across this B point, okay, and the Ising order parameter has a second order phase transition. It's a continuous phase transition. But the Dicke order parameter remains first order, it still has a discontinuous jump. And if we consider the spin susceptibility and the spin entanglement, so both of these quantities will diverge when approach point B from left, but remains finite when approach B from right. And so the conclusion of this part is even though we have both the Dicke model and the transverse field Ising model supports just conventional second order phase transition, but when you combine them, you can have something quite interesting. So this is a case where 1 + 1 is larger than 2. Okay. And of course, you can consider different atom-atom couplings. So I think there are a lot of ground to be to study. Okay, I think that's the end of my talk. Let me thank the people who are involved in the work that I talked about. Eugene and Diego are both former students, and Elon was a visiting student here. He's from a group from PKU. This is his advisor, and I'm also collaborating. Some of the work is also collaboration between my group and Professor Zhang's group from Chongqing University and Professor Gong's group from USTC. All right, with that, I'll thank you for your attention. Let me put this slide on. If you haven't registered, please do.